In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could
All right, hello and welcome to Ether Cosmology, episode 68. Tonight, Shane St. Pierre is going to be doing a presentation on distances on a planar Earth and how units of measurement were derived and how they relate to the graticule. Whenever you're ready, sir.
Oh, great. All right, first let's check the mic level. Can everyone hear me?
Solid.
It
Good to
is?
go.
All right. I think it might be wobbling throughout the night. Oh, wait. Is that better?
It's louder. I don't know that it's better.
Yes.
Let's do this.
Louder, but not better. You were fine.
All right. So there we go. All right. So we're going to do sky miles and nautical miles. Ooh. We switch my stream up. So we got Canva. There we go. Perfect. All right. So
Nice.
essentially, we're going to do nautical miles, right? And we're going to, at the end of this, we're going to understand how distances are measured on the graticule, how distances are measured on a Gleason map, how distances are, synonymous between projections, and how the graticule actually calculates distances on all projections, regardless of how it's visually displayed, etc. So, as we know, it's based on angles to the stars, right? Your observer-centric celestial sphere is a fundamental plane, meaning that you have your horizon, which is flat. You take angles to these celestial bodies as they rise and set, and you translate those angles into a negative value when you don't see them at the bottom half of this fundamental plane, giving you this mathematical concept that we call the celestial sphere, from which the graticule is derived, right? The longitude and latitude system based on angles to the stars. And of course has that mathematically filled out bottom, with just, like I said, the fundamental plane has a negative value that fills out the bottom of this theoretical sphere. So before we go into nautical miles and the historicity here, just know it is simpler than they are making it, okay? They're going to go into, spherical stuff, and we're going to be using how they calculate, and they're going to try and confuse it with all sorts of definitions, but we're going to cut through it and figure out exactly what stuff means, right? So we start with the nautical mile. Now, if you look on Wikipedia, it'll tell you it's defined as the specific length that it is today. That's not what the definition is, right? It's the 1 minute of arc. Essentially, it's a unit of a circle, right? And then you get 60 minutes of arc equals 1 degree. The only thing really in contention is this red part here. 1 degree equals what? Now, that part is completely relative, right? You can have all of this as ratios of a unit, ratios of a circle. This is when you give it a real world value, right? So this is the actual definition of what a nautical mile is, right? So a unit of a circle. If we go into what is an arc second, we can pretty much explain that it is a unit of a circle, right? So they're going to say that this circle represents a sphere. Notice there is no difference between a sphere and a circle. 1 degree, right? You can divide a circle to 360. That gives you 360 degrees. Simple, basic math, right? A minute of arc is 1/60th of a degree. And from that, you can further subdivide it. If you do any sort of astronomical measurement, you'll be familiar with these sorts of metrics, etc. Let's see, am I echoing? No, everyone's good. So it can be further divided right into a second of arc when you get the 3600. Right? Yes, 1 over 3600. That's an arc second. So essentially, right, we haven't given it a actual definition. We haven't given it a metric. We've only just said it's a ratio, right? And we use what is a unit of measurement. The unit of measurement is a standardized quantity, right? It's a unique way to express magnitude of various characteristics. Essentially, they break it down into the metric system, the most widely used system, right? Everyone knows what the metric system is. We'll get into how that plays a role. If we look at the common metrics, right, common units, if you notice, all of these units are defined by other units. So kilometers and meters, centimeters, miles, nautical miles, and feet, feet and inches, meters, centimeters, and yards. You go to yard, that's defined by meters, centimeters, feet, and inches, right? These are all ratios of each other. The whole metric system is in fact ratios of each other. Unless you give one of these ratios a grounded value, these are all just math, right? So something else to keep in mind there. We're going to be going through a brief history of the nautical mile. We're going to be using this book here called The Nautical Mile by this dude, Lieutenant Commander Alton Moody. It's not that old. It's only from 1949. And there's a couple pages in here that I think are noteworthy. So it says that the length of the mile, in this case the nautical mile, remained controversial. So it's always been a hotly contested topic for what it actually represents, the amount of distance that it actually covers. It says, as distinct from the land mile, meaning the nautical mile, of course, being used at sea where there is no land. So how to determine distance when you can only see the stars, I wonder. And is distinct from the land mile. And it said that this is an actual time, because there was insinuating that previously there was a time when they were not made distinct. They were in fact synonymous. So there was only the mile, the nautical mile, which was on land as well as sea, right? Previously, there'd been no distinction between the two. And then, there was an incentive to associate the mile with the size of the earth. I wonder where that incentive came from. Hold on a second. Let's go back here. When they were trying to associate it with the size of the earth, they said that the land mile became 5,280 feet. That's the modern definition, right? Again, defined by other units. Doesn't actually give you a metric of anything. And it says it's not universal. If you go into the nautical mile here, they said, back established at 6 times 20? No, 6,120, and then changed to 6,000 feet. So that's right around this number. Again, still defined by other units. If you look down here, it says the early Roman charts considered to be Earth a plane and did not allow for the convergence of meridians, and that they actually measured their stuff in Roman miles, which was 100 paces. So a pace might be the first thing that we can actually get a metric to, but even that is defined in other units as we get to it.
Cough. 1,000. Cough.
What did I say?
Said 100.
Yeah, you said.
Oh, my bad.
You said it's 1,000
Yeah,
paces. Just to be clear.
1,000 paces. Yeah, that was the actual first metric, denominator or metric equivalent for a mile. The Romans had it at 1,000 paces. That was used for quite a while. And that, if you notice, has no relation to the sides of the earth in any way, shape or unshaped, probably because their view didn't matter, right? They didn't think that they had to define their units of metric in terms of the coordinate system that they were using. They just counted paces. Nice and easy. So again, standard nautical mile to be established based on 1 minute of a great circle. So that's a little bit of a bastardization from what we started with as 1 arc minute, right? Just denoted as the unit of a circle. This is clarifying the type of circle, actually. So it's specifically a great circle of the Earth. Now, that by itself wouldn't necessitate sphericity, right? You can have great circles on planar Earth. You have concentric circles, right? You can even have Earth as a circle. That's kind of how we see it. That doesn't really, that's not mutually exclusive, right? But then you go a bit further, and they said it seemed to use logical to use values employed by surveyors and cartographers so that the measurements on the chart would be correct. So that the number of spheroids on the table have been used by different ones in use today. So literally, they're like, oh, we should make it a metric of a model spheroid. Which spheroid should be used? So then this book is already commenting on it in 1949 that that's how it should have been, right? If we go a little bit further, they said in ancient times, of course, they used the cubit, the foot, the pace, stadium, and the league. And I think that's right in order of how they did it. First, there was the cubit, then they had the foot, the pace is a factor of this one, stadium is a factor of these two. And that's how they did that. And the league, I think, is a factor of stadiums, but I'm not sure about that one. So again, they're just defining units in terms of other units, but they have the first one being, actually pacing, right? So they have, this is a metric of this. So when we get to stadia was just there. If you look at the equivalent, 1.2 nautical mile. If we look back through history, a nautical mile has been defined more or less within the same range throughout history, right? Somewhere between, the 5,280 feet, 4,859 feet, 6,273 feet, right? They've been more or less, theoretically, has been the same length. This one they have 6/5 of a Mediterranean mile, which is how they get to the Roman mile, which is how they get 0.8 of a nautical mile. So again, mostly in terms of other units. And when we get to modern times, it's specifically in terms of the size of the Earth. So this is a different book, but I think this is the only page we use. It's called the Hydrographic Review It's another definition of the Roman nautical mile and the specific accuracy to which they employed it to measure things and map out their cartography, right? So they had the Roman mile used as a mile of 1,000 paces, and they used this to map out the coastlines in particular. You think they would use nautical miles, right? Nope, they're using Roman miles, which is 1,000 paces, which then gets, stadium and all the other units. So we can move forward a little bit. It says that these early miles were defined in terms of other units, and then no way connected to the size of the Earth, as I was saying. Right, so you can still have ratios within ratios that have a system of measurement and comparison without any data grounding it to anything in reality. They grounded it to the length of a pace. Makes a lot of sense when you're trying to compute distances that every man can, more or less average estimate within reason. So then it says, it was not until the period of great discoveries, when charts and greater distances became important to a mariner, that the association of units of length and degrees of latitude became a serious consideration. That the association of units of length and degrees of latitude. So that's how they're trying to get a facet of a great circle. They're going to try and convert a unit of a circle to a length upon a theoretical, fictitious, curved spherical Earth. They're not going to do so with any measurement. They're going to calculate it, of course. Because then it became customary to show one or more scales, and that these lengths ascribed depended upon the size of the Earth accepted by the individual. So that would mean that Romans using paces and having their conception of a flat Earth would have a different size mile than people thinking they lived on a sphere and sailing. Would that make a lot of sense, though, for the mile to be different depending on how you viewed the Earth? Well, not for the Romans, because their mile wasn't dependent on the Earth, right? So if we go to the estimates here, they said, that range again that I was talking about between 44 and 87 nautical miles per degree. So again, today's estimate is 60 nautical miles, right? And they said that back here, they were estimating within an acceptable range of that value. So fluctuations can vary. Now, something that comes into play is that it varies by latitude. It doesn't actually say that here, but that would be a consideration on spherical and planar Earth of concentric circles, right? The outer circle would be bigger than the inner circle and so on. That would be the same in the north as it is on the globe. So that's definitely a factor that they're not mentioning here. They're just saying, hey, we know that it's about this big. They don't say depending on where you are or what's affecting it. As we move on to the last slide of the history here, it says the shift to the minute mile, and universally accepted, did not come about at once. Originally, it was 60 Roman miles, which again, 1,000 paces, which again, 4,859 feet, which is that ratio of 0.8 of a nautical mile, were then considered to be equal to 1 degree. So they said that shift of a minute mile was equal to 1 degree. And then they said, oh, actually, this value isn't correct, seemed to be an error. And I'm sure that they blamed the curvature of the Earth for that error. Let's see. Increased the number of units by degree, and by the 16th century, they considered 70 Roman miles, so they definitely increased it. So yeah, they said that the curvature of the Earth was to blame. So what's the answer to the metric unit? How do we standardize this? Well, in 1735, we have an expedition from the Paris Academy sent to Peru, which is really in the borders of Ecuador, to get the measure of the arc of the meridian, which has to be at the equator, right? So the equatorial measure of an arc of meridian. So then we can provide a more accurate determination of the size of the Earth. And that was completed in 1743. We'll go into that a little bit later. And then the conclusion from this brave discovery and, zealous determination is that the order of the size of the Earth was established, and now we have unit of measurement being chiefly defined as that. So, hurrah for us, right? We bring it back to modern times. A nautical mile is now defined, and when they say defined, they say it's historically defined. That's how you know it's super accurately historic. As we went over, it was not historically defined as this. It was only a unit of a circle as over here. But today, the definition is 1,852 kilometers, which is, related to its equivalence to statute miles. 1 nautical mile is 1.16 statute miles, right? And that's how they define it within the definition. It is also tied to a knot, degree of speed at sea, right? Is a knot is a speed of 1 nautical mile per hour. So they're tying all this together in the definition of the nautical mile. They're literally tying it definitionally to the spherical nature of Earth, because a prime meridian, the length with which they were going to determine which is Earth, is a a facet of a sphere. It can only exist on a sphere. A prime meridian is a line traveling on a sphere from north to south pole, or from pole to pole. It can only exist on a sphere. So to make a arc meridian, this is a fourth of the meridian, right? So it's a quarter of the circumference of the supposed Earth. And to try and measure that, to make it a metric meter, meaning that you're going to tie it to a theoretical arc of curvature that you're calculating and then saying is the Earth. We go back to our book on how they determined the knot. Actually, it's a little bit more descriptive. He says they use the log chip, right? A thin board in the shape of a quarter of a circle, weighted in such a manner as to float vertically. And then the log line, the line attached to the quadrant and knotted at equal intervals. And then they had log glass, which was then thrown overboard and then permitted to run out freely. And as the log line went overboard, when the chip was well clear, the log glass was turned over, and then the number of additional knots paid out while the log glass emptied itself. So they had a definite relationship to the speed, and that each knot was considered equivalent to the speed of 1 nautical mile per hour. So that's more or less how they determined that, and that's how they bastardized that to incorporate it into the length of a prime meridian on the theoretical curved spherical Earth, right? We haven't measured anything yet. We'll get into the survey and how they actually went down there. So what is this actually saying, right? If we look at this orthographic projection, actually, of this dupolar, bipolar model, if you notice, what they're saying is if we have the plane Earth in the middle here, in a circle, then 1 nautical mile is about, they're saying it's this section of this circle, which is 1 minute of 1 degree. So what they define that as is an actual real-world value because they're using a radius, right, and a circumference. When we go over where they get those circumference and radius values in a second, we'll explain that. And to get a better, I think, visualization, let's see if this works. Right, so excellent, right. So we're looking at an arc angle, right? This right here, this quadrant is what they're measuring. This is a great arc. This is the prime, what the meter is going to be ratioed against is 1 length of this, right? When you calculate it out, if we're going to use statute miles, it'd be 69 statute miles per degree. 90 degrees of latitude between the North Pole and the equator equals 6,214 miles. This arc right here, 6,214 miles, which is a geometric consequence of a sphere of radius 3959. So, does the arc length formula require a sphere? Well, no. If we mark it on a circle, right, if we have the Gleason's map, for instance, then we can do the same sort of differentiation and divide it to get the circumference with the same value, the same ratio of nautical miles per degree. You can encompass the same surface area. And it's the same formula whether it's in a circle or applied inside a sphere, meaning non-exclusive, right? And again, this is from before. If we have a observer in the center observing a hemisphere around him, it would be indistinguishable from living on a globe of the same radius. So if we apply it logically to what we just went over, if we imagine, right, there are 24 sections divided on our Earth, divide each section into 15 degrees, and then each 15-degree section times 60 nautical miles per degree would mean each 15-degree section would be 900 nautical miles, and then that would be a circumference of 21,600 nautical miles, which would be the equivalent of the circumference of the spherical Earth in nautical miles, right? 24,901 in statute miles is the same as 21,600 nautical miles because we remember the ratio of equivalence, 1.16 between nautical and statute miles. So it's all the same. We're all talking about the same thing, and we're using units of measurement that are ratios of each other. So if we just go through this bit a second, and then we'll stop for some questions here. I think just want to make sure we're all grasping the unit of a circle. If we divide it out, again, the Gleason's map, this section would be 900 nautical miles. 60 nautical miles per degree, and we can say that actually this is the same area and the same distortion and the same breakdown as the globe. It's exactly the same, as a matter of fact, which we will see later. So the final bit about using nautical miles and measuring distances is that whenever you perform calculations using azimuthal transformations like the one we just were using, whether the Earth itself is considered flat or spherical, the distances like those measured in nautical miles remains consistent. That is because the formulas that calculate distances based on angles to the stars, like Haversine and anything to use cosine of a star or angle to the star, remain valid regardless of the underlying shape of the Earth. Meaning, we just went over how it's ratios of the unit of the measurement of the coordinate system itself. But just without even knowing that, you can say that they remain consistent between transformations. So measurements like nautical and statute miles retain their values because their utility precisely because their definition ties back to the coordinate system, which remains invariant between transformations. So this is a very important slide. It's kind of the crux of the whole argument. Nautical miles remain consistent no matter what. So, any questions so far?
Yes.
Yeah, sorry, you go ahead, Alan.
Okay, so you mentioned a coefficient earlier of 1.6, I think it was, or how they all relate, the different units of measurement.
1.16 to the nautical?
Yes, 1.16, thank you. 0.16.
Yep. I think it's over here. Let's see, nautical mile, 1.15, something. There you go.
Ah, I got you. Okay. Oh, okay, that's a good page. Okay, note that for later. Page 18, or page 8. Okay. All right, thank you, sir. And then I think I had one more question. Okay, yeah. So the measurement of the arc of the meridian, that was around the equator, east-west, right? So that was circumnavigation east-west.
Well, I was going to go into it later, but they actually went geodetic surveying down by Ecuador way and measured it good and hard by calculating it based on the stars again. But yeah, they confirmed it.
Okay, cool. We'll come back to that. Awesome.
Yep.
Continue on, sir. You're doing great.
Stone?
Yeah, I think in Ecuador, because they're on the equator, I think they probably used the sun for timing instead of the stars. That would have made things far easier to do and relate to everything else they've got with regard to hours being solar hours, et cetera, et cetera. But anyways, if you could bug over to slide 22, you're referring to that 900 nautical miles. I think your arrow was pointing way to the outside of the wedge when I think it's actually the equatorial distance across that triangle. Like through the middle of it is 900 nautical miles. Yeah.
I hear you mean, yeah, absolutely. Because
Right?
it does vary by latitude,
Just-
right? As we're going to go into as
Yeah,
well.
just to clarify. Exactly. That's what I was looking at. Okay, great.
Yep. All good points, all good calls. All right. So we'll continue then. We're going to start with this determination, right? So we know, where do we get this from? Who determined 1 degree equals 60 nautical miles? And then, of course, consequently, 1 degree equals 69 statute miles. How do we get that? If we look at our database here, we know that on the globe, perspective applies very selectively to everything in the world: streetlights, boats, mountains, tall things, but not to the stars, right? Everything recedes into the distance and gets smaller with distance due to perspective. On Earth, everything in the world does this, with the exception of the stars, which actually does do that, but at the same exact rate, but for a completely different reason. And that's the globe steel man for how the perspective works as applied to the heavens. Perspective doesn't make the stars rise 69 miles per degree. They say that's all curvature, right? Anyway, where it comes from is how you see the sky. Right? So everyone, no matter what model you believe in, observes a hemisphere around you of the celestial heaven, and things as you observe them appear to rise and set wherever you are. Of course, the sun will make arcs and anti-arcs depending on your latitude and depending on your position on the Earth. But more or less, everybody sees this, right? The globe translates into this into where they think they live, and flat Earth works this into our understanding of our planar reality. Right? So everyone sees the heavens in the shape of a dome, and again, model independent. So if we're going to use basic trig to start, as Alan so eloquently points out, cosigning around the place, right? We'll take cosines to stars all over. It would be something that looks like this, right? We'd have let's put a protractor over us. 90 degrees would be your zenith. Over here is the horizon. Over here behind you, 180. If we had a star that was at 60 degrees, and that's all that we had this measurement, we had a sextant, we're in the middle of nowhere, we said the star is 60 degrees. How far is it to the ground position of that star? If we were to use basic trig to calculate that, we could do so just with this ratio, right? We know our good old friend SOHCAHTOA here. If we're going to use basic cosine law, we're going to do adjacent over hypotenuse. If we're going to calculate it, it would look like this, right? The angle is 60 degrees. course, if you use a unit circle or if you just do it in a calculator, you see this comes out to 1/2, 60 degrees of cosine, right? Then we follow through the math over here that we have the horizontal distance, which again gets answered in a ratio, 30 degrees to the observer's position. So 30 degrees times the conversion factor of 69.08 miles per degree gives us a length of this bottom of this right angle triangle of 2,072.4 miles, right? So we've calculated the ground position of this celestial object using just its angle and basic trig. Right, so the only thing that again was in question is this 69 miles per degree. Where we were getting it.
What slide number is that?
That one is 31. 31. Where we're getting 69 miles per degree is the amount that this precesses, right? As you move laterally on the Earth, horizontally, the stars will precess 1 degree as you move 69 miles. So if you were to move 69 miles this way, all the stars would precess 1 degree this way. Right? If you go towards it, they would go up. If you go away from it, they would go down, right? That's what that relationship is, and that's what they're using to cosine to stars, as Alan says. So again, this is just sort of a breakdown of the right angle triangle, y cosine 60 equals 1/2, if we're going to break it down completely. Just to say that it, again, is an expression of a ratio, and then we use this conversion factor to actually get a real-world distance. And if we ask, say, where do we figure 69 miles per degree? It's like, oh, well, that's because of the Earth's circumference, which, while mathematically true, right, I don't think is the actual derivation. If we say, oh yeah, we know that the circumference of spherical Earth, rather the circumference of the graticule, 24,901. So then, therefore, divided by 360 gives us 69.17 miles per degree. Boom, we're so smart. Okay, well, where does the circumference value come from? How do we measure that? Basic flat Earth stuff. Turns out nobody's measured it, right? We got our scientism starter kit over here, sticks and shadows. We're going to start looking at the sun, measuring the sun, determining the sun, and then determining the size of the Earth, right? Because we're going to look at the sun, measure the sun, and then boom, that's the size of the Earth. No, we're going to look at the sun, measure the sun, and that'll be the limits of the sun that we measure. As we go through a quick Eratosthenes example, notice here, this is all that was measured. Everything else is assumed. The only thing Eratosthenes measured was this angle and this angle. And he assumed parallel light rays and assumed this thing and used this distance measured in stadia at 800 kilometers to actually get the distance. Here, let's do the math. So he did it in stadia. He approximated it to be 40,000 kilometers. What he's doing, though, is the ulterior angle, right? So he's getting a 7-degree difference, saying that's 1/50th of a circle, and using the math to using this 800-kilometer known distance between this pole and this pole, Syene and Alexandria, and he's computing that based on that, it's a 40,000 kilometer total circumference of the graticule, as we were talking about before, and therefore he's measured the Earth. No, you've measured the sun, right? You've looked at the sun, you've assumed things about the sun, you measured the sun rays, you looked at shadows cast by the sun, you've measured the limits of the sun on the Earth. But
how did they talk to each other to correspond with the light at the same time? Huh.
I want to know how the guy paced out 500 miles through nothingness in Egypt, going up the hill with and without the river, through everybody's farmland, through all kinds of unbelievable hordes and masses of savages. I'm just taking a length, boys. Don't mind me.
If you look into it, everyone says the answer is they simply already knew. There's nothing about how they found out. Did they measure? Was it calculated? It was just known. It is known, guys. You know, like from the...
It's 500.
It has been stated. Did you cover also that there's no documentation of what a stadia is? Just modern scholars have agreed to make it a ratio of the terrestrial meridian.
Again, yeah, it's always back to a ratio of itself. Stadia, of course, is just it's kind of a made up thing, I think, in my mind. I was going to go into that, but in the realm of fake Greeks, right? It's kind of they say that it. Let's start with Ptolemy, right? Ptolemy wrote the book Geographia, the history of all cartography, where he wrote longitude and latitude measurements of the whole known world in useful stadia. We had longitude in stadia, and latitude in stadia, and he helpfully wrote down the GPS coordinates of all the world, all the landmarks, all the buildings, all the hills. I mean, how he would know to do that so nicely so that we would have a nice GPS filled out reticule, very nice of him, right? No. Honestly, stadia is just another unit of measurement that is a ratio of all the other measurements. And once you have, as we saw, the metric system is all ratios of each other. What's one more ratio, right?
What's the ratio between friends?
There's more breakdown of the Eratosthenes. I say this all the time really quickly when I'm going through Globers. I'm like, oh, it's because, measured a 7.2 degree difference and then knew that the difference between 800 kilometers and 360 degrees over 50 gives you, 40,000 kilometers. That's the math. You can go through that, but it doesn't mean 40,000 circumference of what, right? Of what is my argument all the time. What did you measure? You're not measuring the Earth. You're looking at the sun. You're measuring the sky. Could it be that you've calculated, say, the circumference of the limits of the sun? Right? If you were in Alexandria and you saw the sun and you took some angles, you might say this green circle would represent where you would see the sunlight, which is almost the actual terminator line in real life. So if you live on, say, a flat Earth, right, and you're over here in Alexandria, and you measure the sun, then this green circle would be the circle that we just plotted that would have a circumference of 24,901, right? About right here. So Eratosthenes looked at the sun, measured the sun, calculated the sun. But if you look at their history, he calculated the size of the Earth that way. So we're already measuring units of the graticule with other units of the graticule. Let's see. Let's go through here. Right. So as Stone was saying earlier, the 69 miles per degree does not actually apply equally to east-west as it does to north-south. There's some reasons for that. Funny enough, if we look at our actual projection, it's by definition only applying this way. So I know that we don't live on a model, right? But if the world was set up as the Gleason's map is, then the actual distances as computed would be absolutely accurate going north to south. So you could do 69 miles per degree all the way out, and that's consistent, which is the same thing on the Gleason's map, right? This is, the line of longitude that is measured exactly distant from the pole. So does that mean I can go this way on this circle and get 69 miles per degree? No. No. Right? So maybe at the equator, as we said before, that would apply. And then at latitude dependent north or south, it starts getting different, right? It's a different application, which is how the Romans had a different number and they all had a different number, and it was more or less above. It was, getting smaller, getting higher, and they decided, oh, that wasn't quite accurate because they were all at different latitudes, right? So they're all trying to do the same measurement to get the same distance. Now that we know it only applies this way. So again, if we look at the history of the meter and how the meter was the first actually unit of measurement to be ratioed against the graticule, and again, we went over the 18th century after the French Revolution. It was the Meter Day Archives Convention in 1799. That's when they were ratioing it against a platinum bar. But this was after that. They had first done it during the French Revolution to be 1/10,000,000th of the distance from the North Pole to the equator along a specific meridian passing through Paris, right? So they went down to Ecuador to measure this. They had to calculate it based on that form of geodetic surveying. And they said that so the meter would then henceforth, always and forever, be defined as 1/10,000,000th of the distance from the North Pole to the equator. And again, it's all the calculating Earth's curvature errors resulted in our meter being wrong. So we're going to have to refine that. Oh, what do? Well, we'll send down, after the meter convention, we'll send down a dude to get the bestest measurement, right? So what that means then is if you take the known, measurement of 69 miles per degree, which again, they're getting from the circumference, which they're getting from looking at the sun, and you say 90 degrees of latitude between the North Pole and the equator, right? 9 degrees of separation. So 90 times 69 miles per degree, 6,218 statute miles from the North Pole to the equator. And if you take 1/10,000,000th of that, as we just decreed before, then that equals 1.0007 meters. So of course, this is in miles, convert miles to meters, and then you get it actually 1/10,000,000th of that. It comes out to be 1 meter. So literally, the distance calculated from the precession of the sky, not measured on Earth. So again, we're looking at the sky to get this. So we're assuming this, right? We're calculating this, and then we're saying all measurements will be a ratio of this. So 1/10,000,000th. Now, It goes through some historical recontextualization, right? But the math that we just went through will forever and always define the meter. This will never not be the case, regardless of how they say they ratioed it later, right? So the thing about history is they recontextualize it. They don't change it. They say, oh, well, we updated it, right? So again, 1791, 1/10 millionth of the North Pole to the equator along the meridian through Paris. 8 years later, well, actually, we're going to do a length of a platinum bar, and we're going to hold it in the meter archives, okay? 100 years later, it's actually, well, we're going to do the distance between two lines on a palladium alloy, right? 10%, known as the International Prototype Meter. And then later, we're going to do actually wavelengths of orange, red light emitted by krypton in a vacuum. And that wasn't cool enough in 1983. We're actually going to use the length of light, the length of the path traveled by light in a vacuum, which we're going to say arbitrarily, for no special reason, 1/299,792,458 of a second, which actually, as it happens out, these all still equal this figure right here. So because, all right, we're gonna ratio it as a 1983 definition. We're gonna call it the length of path of light traveled by a vacuum in 1/299,792,458 of a second. Then we do this math. We say, okay, 69 times 90 equals 6218. 1/10 million of 6218 is still, oh, wait a second, it's still 1.0007. Oh, man. So none of this matters, and it's still only ever defined as this initial metric and measurement. So if you find a ratio of light speed that still equals 1/10 millionth of 6,218, did the value change at all? No. This is historical recontextualization of what was already done. So the final definition, they say they fixed it at 299,792,458 meters per second, and they solidified it, and it gets reified all the time. Okay, so that's the meter. Now, if we look into how they did that survey, remember, because they sent this guy down here, they're like, go to Ecuador, we're going to get the bestest Earth measurement we can so that our meter convention will be on point. So they go through, and oh, look, this is the French geodesic mission to the equator, also called the French geodesic mission to Peru, or the Spanish-French geodesic mission. It was a famous mission, literally carried out to performing an arc measurement, measuring the length of a degree of latitude near the equator by which the Earth's radius can be inferred. So the first geodesic mission, or geodetic, carried out under modern scientific. So they went down there, and we know that the definition of geodetic surveying, as we know it, is that the Earth's dimensions must be previously known to enable the exact computation of positions, and that computations of a previously known value of Earth's dimensions must be known. Then how did they measure it for the first time? By confirming it and already knowing it. They went down to measure it, right? Because we're trying to find the best measurement of this arc of the parallel over here. This arc, we're going to measure 1/10 millionth of the distance from the North Pole to the equator, and we're going to definitely know that, and we're going to measure that by already knowing it. Huh? Wait a second. we're gonna go figure it out. So they went down there to reconfirm what they'd already calculated by using specific and common geodetic surveying techniques, as we know. Measuring large areas using planar surveying up to a point, essentially stitching planar surveys together, necessitates a precise understanding of the Earth shape, as we know. So when they went down there, they measured arcs of the Earth's curvature. More accurately, we can say they looked at the stars and they calculated based on what they already thought they knew. And then that whole measurement is what's known to give the Earth's circumference that we know today, which is now what's defining the meter and what we're using to measure things like feet, miles, statute miles, yards, etc., etc. If we return to our buddy Eratosthenes on how he knew the distance, actually, when he was calculating it, if we look to our boy Wikipedia, he's like, he already knew that this was how long it was by knowing the distance between Alexandria and surveying, which was measured by professional surveyors called pragmatists. Oh, cool. Well, they had it figured out, guys. They already geodesic surveyed it out. That's how they knew how long the distance was in the first place, which tells me they had just calculated it based on the assumption from looking at the sky in the first place, right? So, to bring all this history into our modern understanding of dimensions and distances, right? We know it's because everything's around the globe. That's why it works, right? No, it's because of the graticule, which is a spherical coordinate system that people commonly mistake for the globe. In fact, I would say most globers arguing today are incapable of distinguishing between the graticule and the globe. I mean, I can understand it's difficult. They're both theoretical nonsense things that don't exist in reality, that are constructed purely out of math and models, but they are different. They're not synonymous, right? The graticule is the gridded network of latitude and longitude. This is the pattern of meridians that form the spherical coordinate system, not the surface of the Earth, right? It is the coordinate system of longitude and latitude. The Earth is not longitude and latitude, right? Latitude and longitude are coordinates. Go over here, the geographic coordinates, which is how we get the geographic graticule, right? It's what I keep calling it. It's important to note that latitude and longitude are not a map projection. You have a question? No. They're a set of spherical coordinates used to reference positions on the Earth, right? And they're the basis for all projected coordinate systems. So when we're using a map or we're talking about the graticule, everything is determined by latitude and longitude, right? East to west angular distance from the prime meridian, which we already know and measured, of course, super accurately, and the north-south distance from the equator. So this is latitude is angles to the stars, longitude is a time function when we get to it.
I do have a question, actually.
Yep.
You said that the graticule and the globe are not synonymous.
Yep.
Is that because they have to constantly correct to the graticule to make it idealized?
Well, latitude and longitude are just a coordinate system, right? To tie that coordinate system to reality, they need a datum, and a datum would be like the GWGS84, NAD83, NAD, all those spheroid, ellipsoid models that get confirmed and reified during the surveys. That's what theoretically would tie it to Earth, right? But we know that those are also based on angles to the stars, corrections to coordinate systems, triangulation issues, all sorts of math that would bring it back to the latitude longitude system. So the graticule is the coordinate system, and the Earth would be the Earth, right? So without the datum, which they of course put in tie it to the stars, then the coordinate system would have no relationship to the Earth. Right? So they would be separate. Like, but a glober wouldn't know the difference between latitude and longitude and the Earth, right?
Right.
That's what I'm finding anyway when I'm trying to ask them to differentiate it. Any other questions?
Continue, brother.
All right, we're almost getting to the end, I think. Be about an hour. So garbage in, garbage out. I mean, sorry, a NAD83, WGS84 geographic spherical datums in, and then geographic spherical datums out, right? You put a coordinate system in, it comes out in the same coordinate system. This is just basic foil, right? So all maps are projecting the graticule. They're translating the graticule. They're distorting the graticule. They're projecting, translating and transforming the graticule. They're doing all sorts of these projections, but it's all based on projecting a sphere onto a flat plane, right? The contention is, what is that sphere? Is it the spherical graticule, the coordinate system that we've been going over based on angles to the stars, or is it the theoretical, fictitious, definitely measured curved Earth? That's the contention. Globers think, of course, this is the Earth. This is why this all works. And if you look into it and actually know, maps are projected coordinate systems. What coordinate system? Latitude, longitude. So right in the definition, you'll find that's not the case. And all of this is a facet of the stereographic projection of the graticule onto a flat map, which of course has its basis in the celestial sphere. So that brings us to our boy, Alex Gleason, which is, created the flat Earth model. Wait a second. Or he patented a globe map. Wait, that's not right. What did he do? Oh, wait, no. Yeah, he came up with the azimuthal equidistant projection when he patented it using the same coordinate system, of course, the same spherical graticule, and he put it as is with a sun calculator on it. So we're going to go over that map a little bit. We're going to go over what it's used for, how to properly use it, and how to properly not use it, right? We're not going to go into all the types of map projections, but just know that an azimuthal equidistant projection, along with preserving directions, which is of course inherent, right? You project from a certain point out, azimuth is preserved. It also straightens or rectifies great circles. This is very important because we started with that sphere and we had a great circle, right? The nautical mile is defined by a circle. They tried to redefine it as a great circle, and then they tried to use it. So we're gonna pay special attention to that. Here's how the Gleason's map should look, right? It comes with these two arms. I forget what they're called, articulator arms, maybe, I forget. But they're supposed to reference the grid of which the map is a projection of. And using these two arms, you can tell longitude, you can tell the difference between two places, you can tell the time, and you can tell all sorts of things. So we're going to go through that briefly right here. But first, let's look at the sun calculator portion. So it's got these two markers on the Gleasons if you look at it fully, and we're going to blow those up. And they say the June solstice and the December solstice. So it says, this is essentially giving you the guide for the sunlight on Earth and how you can calculate where it is and how you use the math to figure it out. What I wanted to call attention to, though, is this part over here. It says, there is no sunlight beyond 80 degrees south, but unknown regions of ice. Now, I think with recent events, we can question that, right? We had our boys down there by 79 south, and there certainly looked to be a lot of sunlight where they were. And certainly you could imagine that one more degree southward, sunlight wouldn't suddenly stop. But we were only at 79. I would say it's good evidence for this not being the case. However, the rest of it, I think, is super accurate because it only deals with the ground position of the sun, which is how they're ever going to use it to calculate it. If we were to read the back of the map, it has instructions, I think, on it. And it says, let's see, the letter G articulator, a lower indicating arm. So it gives an example, the graduate edge on the line. If you're in New York, the 15th meridian, they use the time arm with London. They get a time difference. They subtract the time difference. They get a longitude. They use the longitude to determine the time. So we're going to go through an example. But if you were to get the map and print it out, these are the instructions on the back to show you how to properly use and get distance. And it says it's a longitude and time calculator, right? And it goes over based on the Greenwich Meridian, which, of course, established by the Royal Society back from the Board of Longitude, when they first decided the coordinate system back in the 1714. If you look at this part, it says based on the altitude of the sun and the angle of 45 arc of the heavens. So it divides the Earth from the great circle, and it uses, angles to the sun, essentially, to map it out. If we were to use it properly, right, we would use these arms, and we would line them up, and we would actually take an angle represented here and multiply it to get the time. But before we do one of those, let's look at what gets really confusing about this map is the legend, right? There's a legend on the bottom, and people go, oh, I know how to use that. Right, it tells me right here. I'll just start lining that up and drawing straight lines on this map. And like, if I want to know a distance, I'll just drop my ruler and I'll be able to tell. Absolutely not. That is 100% not how you use the legend. That is not how the scale applies. That is not what this tool projection is for. That is not how you measure distances on this map. We went over, right? 69 miles per degree this way. Works perfectly well along each meridian. It also works perfectly well laterally on the equator. Wouldn't work anywhere else. It goes left or right, right? So how would you use this legend then? Well, you'd do this. You'd use the arms, and then the legend is, of course, rule is meant to do it right here. And that's how you'd measure the distance. That's how you'd properly apply the scale at the bottom of the Gleason's map to get distances, right? Now, to get distances, say, between this city and this city, we'd have to do something else. We'd have to do some actual calculations. We'd have to use the instructions on the back of the map by using a known time and a time calculator, right? So again, we're stuck with that UTC being based on the prime meridian through Greenwich and the Royal Observatory there. Whatever, we're going to use that to use the time difference calculation, right? When you know it's a time in New York, you can convert longitude to time difference using 1 degree is 4 minutes of time, meaning 15 degrees is 1 hour. That comes from the Aldinger hour conversion when you're doing right ascension declination to latitude longitude. So inherent in this projection and Gleason's map, when used properly, is a longitude calculator, a time calculator, and using these two together, you can get distances, positions, and anything you want using the map. Just know that you add hours when traveling west, subtract them when traveling, add hours when traveling east, subtract when traveling west. For an example, right? if we position it at 0 degrees, at Greenwich limit, and we position the second one at 74 west, so pretend this one's over here, pretend this one's over here, we have an angle between these two, which would be about this big, and this angle would be about 72 degrees. That's how you're supposed to use this. You'd set this along the destination city, you'd set this along the other city, you'd measure this angle, and that's where you get 74 degrees. Use the calculation with the time, 4 minutes over 1 degree equals 296 minutes. Of course, that's 4 hours, 56 minutes. So now you know the time over here is 4 hours, 56 minutes above what it was measured over here. And that's how you'd use it for a time calculator. So use the the hour angle conversion and 1 degree equaling 4 minutes, right? And you use that calculation. To get the longitude calculation, you would use this differently, right? You'd use 45 degrees of longitude difference. You'd use the same sort of conversion factor, but if there's a 3-hour difference, it's only 180 minutes divided by the 4 again, right? To get longitude difference. And then it says Earth rotates 15 degrees per hour, but of course, sidereal time applied the same way. You get 15 degrees, 360 divided by 24, you get sidereal time. Each degree, 4 minutes of local time. So then you convert, and you get the actual difference. The other way.
So the 4 minutes is equal to the 1 degree of longitude. Got it.
Yep.
Okay. I was like, where did you get the 4 from? I just saw it at the bottom. Thank you.
And just note that sidereal time, right? So when you have a position of a star, you only know where that star is at that time. And then when you have the time, then you have the right attention, right? That's the whole right attention component.
Right.
So we're gonna watch this, I think, couple minutes of this. It's really apt and on point. It's on the Gleason's map. It's how to use directions correctly and how to gauge it with the sun, right? So as it's a sun calculator, might as well look at this. Ooh, I think I need to share with sound again real quick now.
No one tried to talk during the video.
Yeah, I think it'll echo everybody. I tested this out earlier. So let's see. Let me get back to it here. Okay. Change. All right. Can you guys hear this? And just to bring us back to this post.
Yep.
All right, cool. Post I made a while ago. I think this is so spot on. All globe evidence is just people misunderstanding what they see in the sky, right? Everyone knows you need flat baseline to take any elevation angles to the sky, but also the sun's ecliptic and the path it takes and the arc it makes in your hemispherical vision is what the baseline was for creating the globe in the first place. Of course, hundreds of years of celestial observations is what created the globe model to match these observations and explain them, right? Let's get into the best piece of evidence for the globe, in my opinion. No lie. And I say that for a couple of reasons. First, because most people don't have the underlying knowledge to dissect this in a way that makes sense to the general public, right? Most people are going to believe what this diagram is about to show us. And I think that's why it's a strong point. And again, if I was a glober and I wanted to be the best glober I could be, I would stand on this point 100% and just argue it incessantly, right? I would never give it up. I would never acknowledge what I'm about to show you, though. So first, let's watch it and let's comment on what it's showing us, right? So we have 3 observers, and this kind soul, this kind anti-flat earther has named them Whitsitt, Shane, and Ted and Bill, right? And we have, it's like the sun or the moon, doesn't matter which, right above, say, Ted. Right? And Ted's looking at it from south of it, right? Because he's south of where the zenith and the ground position should be. And then we have Whitsitt over here in the west. And the first mistake we have here is you see this arrow right here? When you're drawing a line to do cardinal directionality like this with a ruler on an azimuthal equidistant direction preserving projection, this destroys this map. This is not a direction. This is not his west. West has to be circling like this line or it's not west, right? East and west directions are only preserved from the center projection point. So in this one, from the pole in the center, that's how you preserve directions. From nowhere else are they preserved. Are circles. If you don't maintain a circle, it's not directionality. So this is already wrong. This is not in the direction of this person. We'll see it. When we go through how it works later, we'll pay special attention to how that actually works. But for now, just note that this right here has invalidated the entire example. All right, next. Again, line. Can't have a straight line drawing directionals. This is not a direction, right? His direction has to be maintained around the central axis, or it's not a direction. That's the only way this projection works, to maintain directionality as one of its functions. And if you're going to use a projection and then destroy its base function, it's retarded, right? So that's not what you're going to do. So he's showing this, right? The other side of the sun, he's saying you should see the other side of the sun as well. So we'll address that separately, but let's get into why this is easily explained on flat Earth. We got it set up on their starting position over here, and I have it sort of mirrored over here. Now, taking a look at it, right? I don't really know where Shane is supposed to be, honestly. It looks like he's in the ocean somewhere in this dark area. I don't know. We'll just go with it, right? So we got South America, we got Australia, we got Africa. So what's it over here? First mistake, like I said, is his pointing this way to see the sun that's over here. Nope, sun's over here, right? Super easy. Sun's over here. This person sees it setting south, right? Because it's their summer, so it sees it seeing south of west, right? Rises a little bit south of east, and it sets south of west for this season, for them, right? That's how he would see it. You see, rises for him, sets for him, right here, and his is an ecliptic view in this band of him. This is the one person. So this is Witset's view, right? And here's the sun over here that he's looking at. And if we move our observer to where Ted is, right over here, right? Ted's behind it, over here. There you go, Ted. Hey, buddy. Ted's behind the sun. I haven't moved anything, right? I've just moved my observer, and Ted sees it right about where this angle is, right? That's not bad. Right about here, 45 degrees, cool. Swing it around. Let's go find Bill. Bill's at the same. Let's go this way, right? Bill's over here. Says that his directionality for this sun is he's looking directly this way. Again, wrong. That's not how it works. Maintaining directionality has to be curved. It's a circle. And if we look through where he would see it, it's exactly here. It's exactly where he would see it. Setting, or just about here. Not setting, but and his ecliptic, right? See how it goes like this for him? There you go. That's how he would see it, and that's where he sees it currently. Now, we go to our last observer, Shane, who is somewhere in the ocean, right? So he's over here somewhere. Looks like that's cool. The sun is still over here, and again he has an arrow drawn this way, breaking the direction preserving azimuthal equidistant projection of the celestial sphere or the geographic reticule, right? This is not how you use this data when it's presented. You're violating this. This is not a right direction, right? That is wrong. On the globe, on flat Earth, in reality, on the model, wrong in all cases, right? No, it's not how you do this. The person doing this doesn't understand this projection or cartography. Anyway, we can bring it to our last observer. We see that he sees it as the sun's over here, exactly where he's supposed to see it, rising in his little azimuthal grid of observability. Actually, let's put it there. There we go. So if we take it to where he is seeing it from, again, this is Shane, and he's seeing it. Look at that. Perfect. Just as it swings around and goes away. Swings around and goes away. So this model adequately explains every sun angle from all over Earth to every observer. If you just put in a time here, it'll do any time, right? Do now. Now is the current time. Here we go. Don't pay attention to that. That's just when you're scrolling through the database, right? When it's scrolling through the available data. If you hit now, this is now. This is exactly now. You can do the same thing for Latin long and coordinates and anything you want. You don't have to use the sliders. Right, so that's not how you use that map. You don't draw straight lines from one point to another. That's not how you measure distances. That's not how you would view celestial object without accounting for your curved hemispherical vision of the sky. This is all wrong, a huge straw man, and the best argument the globe usually has, to be honest. So that's why I put that in there. It's good to be able to defend it. I think if I switch it up, that I think I shared unshared audio. So then that brings us to this point right here. Quit comparing celestial sphere to geographic graticule as if it's an insult or an attack on me. That's retarded, right? This is the same data as this, which is the same data as this, which was modeled from this, created from the celestial sphere, and projected into this, right? These are all the same. These are all the same. To say, oh, this one, the distances look weird. Well, tough. It's the same as this one. It's the same as this curved geodesic. Remember, this 6218 is the same 6218 for this map, right? Identical. So you can complain about it. You can misunderstand it. You can make memes that are pretend attacks like this guy did, but it doesn't work, right? This is silly. Now,
it only
this
works on the globe.
Somebody used this misinterpretation, right? I think everyone here should be able to see what the problem with this is, but I'll go through it just so we know. He says, how we know Earth isn't flat He's using this flattened out graticule, spherical graticule projection, saying that how we know it's not flat. He's saying the distance from the North Pole to the equator, 6214. Oh, we agree with you there, right? 69 point whatever times 90 gives you this figure. Cool. But then he messes up and he forgets that this is a direction preserving projection, and also it straightens out great meridians. It corrects or rectifies great circles from the North Pole. That's part of its aspect. Remember that it does this. Great circle arcs are rectified and shown as straight lines. So can't forget that it fixes or it rectifies great circles. So this guy is saying, oh look, now if we make a great circle from this non-straightened out circumference, it gets us a sphere of a different circumference. And it's like wrong. This is displaying the same distance as before. You don't get to then remake another circle based on that equatorial circumference. That's retarded, right? This is a retarded application of a misinterpretation of what this tool is. This distance is the same on the globe on this projection because, again, they're all the same. To tie it into, for a good example, right? If we take one of the flat Earth flights from that book, coffee table book from Flat Earth Banjo, we'll just say Air France flight AF-116. I think I picked it because it's a good distance and it's a nice line that I get to draw. It's something like 6,000 miles, right? 6,000 miles, 9,200 and whatever, 85 kilometers. Here's where it started and left from. And then if we plot it out on different maps, right? Like this one, 6,000 miles, 6,000 miles, 6,000 miles, still 6,000 miles, 6,000 miles, 6,000 miles, right? It's the same every time. So when they say, oh, look, if you draw it on a Gleason's map and you think it looks goofy and you're going to try and measure it using the square thing on the bottom, you're going to try and misapply a ruler as a scale, you're going to get all fucked up because that's not how you do it. The distance on any projection is actually determined by the graticule, right? The difference and the distances between the points of latitude and longitude only, not by the colored graphical depiction of the line. It doesn't matter what this line looks like in reality on the graticule. It's always the same, right? It's always the same distance represented. So, oh, I think I have another video at the very end. I shouldn't have unshared it. All right. So let me share
Love
it back.
that swirly northern projection you got there. That's cool.
I was I was looking for the goofiest ones. I think there's worse ones. That one's cool.
That one right there. That's fucking
Yeah.
cool, man.
Yeah, actually, there's a better one that Mr. Robert Bennett shared with me that we should probably watch, actually, because it's another aspect of surface area tying to a surface from a sphere to a circle, and it uses a prime meridian, so it lays down. I think it uses some mathematical law where it translates a sphere to a circle of twice the radius, and it keeps the area the same. I thought it was really cool, but it looked exactly like the swirling prime meridians from the north. So let's reshare with sound this time. Share, change windows. With sound. All right, so can you guys hear?
What is the definition of
Yes. You guys could
What
hear
is
that?
the definition of a meter? And why does it matter? Well, the original definition ties the unit of measurement to the Earth's dimensions, inherently.
You go, AI guy.
That's all right. He pretty much says all the stuff that we said, actually, now that I'm looking at it. That video is a summary of everything we just did, but we don't have to watch the AI guy. We did nautical miles, units of a circle, right? We started off with its actual definition, which is 1 minute of arc, right? So it's not specific to any great circle. It's specific only to a circle. And then the recontextualization of that. Oh, audio echo for me too? Okay. Does it echo me? That's terrible.
No.
Oh. Canva, no audio. Okay, cool.
Testing. Yep, you're good.
So, questions, guys? Questions, concerns?
Who was that anti-flat earther? Just curious.
Which one?
I don't know, the one that was basically drawing straight lines on the AE map.
Oh, it's someone on Twitter. he posted, I think it's like Pythagoras or something. He's posted that like 7 times, so I took it and made a video and use it as a tool. Because, they always like, Flurf, it's my secret weapon that if you draw straight lines on something that uses a circle to preserve azimuthal directions, and then you use a point that isn't the center to try and make a direction gauging correction. It's like, how retarded can you be? Pretty retarded.
So pretty much all those arguments that use an AE map that show flight paths that say, well, look at it on an AE map. Look, if we draw a straight line, it'd be way faster. We should probably throw that argument out then.
Yes.
Okay.
But so what those arguments
Very
are for, in my mind, those are arguments of proximity. So like if the plane starts over here and then here, like the way that the AE map lays it out, you can tell, look, it's not going to go this way because it's not a globe, right? It's not going to go this way. It has to go this way. The arguments of proximity. When we saw the one that Ruhif showed us that actually was in our favor, it started going like this and then it went like this, right? So it follows what we think of in practicality and would make arguments of proximity. So that's how I think the flight path should be treated. Certainly not by drawing long lines like this and then saying, look how much further it is. Right? Definitely don't do that. That's silly. Also, drawing straight lines really anywhere on this is not a good representation of direction. Technically, if you were to draw a straight line on a Mercator, right, that's useful, and then you could translate it to this, it would be a circle. You would see it, you would see a straight line as a circle on this map, unless it's from the center outward, because it rectifies great circles from the center outward, but not all the other great circles, right? So if you draw from a point from here to here with a straight line is not right. Right? They're all doing circles. Because remember, if you're maintaining east and west as a bearing, you're not doing a straight line, you're doing a circle.
Yeah, I gotcha. So, when it comes to southward, like moving southward on that map, that would be the only straight line.
Depends on how you're finding south, right? Because then you're using a compass, then you're working with the magnetic field lines, which of course are in flux, and then you have your magnetic declination readings, be the difference between geographic and magnetic south, and then you have, of course, the magnetic south pole doing all sorts of wide variations in that flux field, so that you have, say, you tell your compass to read south, and it sends you 120 degrees back the way you came. Oh.
Right. But just conceptually speaking, that would be the only straight line.
Yep.
Yeah. Cool presentation, bro.
Sky miles, man. Everything is actually still measured in sky miles. We just call it meters. Is the only thing that's ever been ratioed against is that terrestrial meridian. And it turns out they did another fake geodetic survey where they pretended to measure but looked at the stars and calculated hard. Like when I found that out, I was like, oh man, every single time that you think they're gonna measure that Earth curve, they're like, look up. Got it. I'm trying to find that slide. Like literally this guy, right? The French geodesic mission, the first one ever. I was like, oh, how are they gonna measure it? Wait a second, I know that word. Wait a second, I know how you do those surveys. You compare to the previously known ellipsoid models and you correct like crazy. Oh no.
What ellipsoid model was back then, though? Curious.
Yeah, so there's not really much information about
Oh,
that.
I got you.
Oh,
Yeah, so from the
Owls,
Supplemental
ready.
Nautical Almanac in Ephemeris and American Ephemeris, they gave like the history on how they came up with the correction angles for the Nautical Almanac, and this was by royal decree or whatever. So this information comes from the British Crown. Anyway, so in the history, they say that there was 2 models that they had suggested. One was the Hayford spheroid model, which was earlier in the Prezi. I think there was different circumference values that were measured or calculated out, rather. And anyway,
Yep.
there was a couple of different competing spheroid models that they would use, and then they would basically take zenith measurements to stars, and anytime they were off, they would take the difference, and then that difference became how the Earth was more flat or oblate or curved. They called it the eccentricity of the of the deviation from the perfect sphere is how, you know, they came up with that from these deviations from the stars where they expected them following cosines because they couldn't complete the 90-degree triangle.
Gotcha.
Yeah, which is another good one, right? Like the
And
ratios. They're using trig to get ratios only.
Yeah, and the whole book, like in the first 8 pages, it talks about deflection of the vertical. So they just assumed that based on the reason why they couldn't get that calculation to work out, to get that zenith measurement, they just assumed it was due to the shape of the Earth.
Must be a little oblate over here, you know? Makes sense.
Shout out to the Queen of England.
Shout out.
Dude, whenever you got to measure the Earth, just get out your sticks and shadows and do Eratosthenes style. Assume, and calculate. Nailed it.
Well, that picture right there explains why Eratosthenes didn't quite get the figure right, because his sticks were all curvy.
Use twigs instead of the big lumber pieces.
Yeah, my feet
Well-
hurt after that month of walking. Let me tell you.
Dude, as well is probably crooked too. Dude can't build nothing. All right, well then,
Any other questions?
if not, then we can get ready for the double feature and do Stone's presentation, which means I gotta switch all my streams over.
Yeah, if you're tuned in on YouTube right now, stay tuned for the upcoming scheduled stream. Stone's going to do a presentation called Refutations and Retractions.
Retractions and refutations, actually. Close enough.
Thank you, sir.
Semi been
Take a
retracted
coffee
again.
break.
Nice. All right. Well, thanks everyone.
Yep, great presentation, man. You so many missing pieces are connected there, and units of measurements related to distances on the ground and how they're all related to the sky, actually. And it all makes sense now how it all relates together and why all these different units of measurement that appear to be independent of each other are just ratios of each other, which are just ratios of the same thing. It's the classic bait and switch, and they give us like Coke and Pepsi, right? We've got American Freedom units, and we got the metric unit, and we're like, oh, dude, we're under the illusion that, like, you know, one of these was independently derived of the other or something, and they're not related to distances of the sky and the.
All they had to do was leave it at paces, right? But they couldn't.
Couldn't do it.
Couldn't do that. No, had to make it a ratio of a terrestrial meridian, a thing that doesn't actually exist in real life. Something that we can only mathematically compute. Wow. Imagine that. Nice. So I'm going to end out this stream and then I'm going to start my new one.
Oh, okay.
Oh, you
was gonna
just keep rolling in.
No. I was gonna say tomorrow we'll be doing some TikTok stuff. We'll be hosting a TikTok space.
Nice.
Yes.
Nice.
All right. So stay tuned for that and see you tomorrow, or in like 15 minutes.